Hi, this is Tony and Ian from Tektronix. This video is going to be something a little different. We are going to show you a demo we did in front of a live audience a few weeks ago. Tony, do you want to set the scene here?
Yeah, in a live audience it was. It was at the Access Academy with all the 8th graders, right? And Judy Burke was able to have a oscilloscope donated to them. And she came to us and said, you know, could you guys do a quick demo of how you would use the oscilloscope?
Right, and we decided we'd work a little silliness into the presentation.
It wasn't a little more than silliness, too. There was some danger.
Right, well, for the presenters anyway. Now, we want to stress...
No, just the presenter.
Just Tony, right? We want to stress that the robot that we set loose was targeted only at Tony. The audience was perfectly safe.
Yeah, and it wasn't really until we added this fork to the front of it that it became very dangerous because it was heading to my eye. But you'll see this in the demo.
So kids, if you try this at home, don't arm the robot.
So, Ian, what did we do in the demo? What was the main thing that we kind of showed in the demo?
Well, we showed how to do a duty cycle measurement with an oscilloscope. And for those not familiar, a duty cycle measurement, if you imagine a signal that's turning on and off like this, the duty cycle is the percentage of time that the signal stays on. So in this case, this signal's on about 4/5 of the time, so the duty cycle would be 80%.
Okay, that makes sense. That sounds like a really helpful demo that people could look at.
I hope so.
So we'd like to thank Judy Burke for setting this up and getting the oscilloscope to the school. And then the teacher, Mr. Garcia.
And Brett Nelson of Portland for building this awesome robot. So without further ado, here's the demo.
Enjoy.
So it's a lovely robot, but with the addition...
We're going to change it.
We're going to change it. With the addition of a simple spork, we are going to turn it into a pain machine. Now this is a very dangerous robot because it's got a spork. This could really put an eye out. And
Ian, careful how you're talking about that because it's going to be my eye that might be put out.
that's true. Yeah. We're going to set the robot chasing after Tony.
Okay, is everybody... Wait, let me get the first aid kit just in case. Can
we get a volunteer? Does anybody not mind the sight of blood or guts?
I don't.
Or like pop?
Sure. Okay, have this prepared just in case Ian here, the engineer, doesn't figure this out right. We've tested this a couple of times and it's...
But you never know.
Yeah, I don't
now,
know.
just in case, Tony, have you ever thought of becoming a pirate if things don't work out too well today?
I have been one before.
So this robot is programmed in this programming language where the pieces of the program clip together like little puzzle pieces. At the start of my program, I want to set the power of my motors to 3. We'll get to what these numbers mean. And then I want to turn both motors on. The robot has 2 wheels. We're going to wait for 3 seconds, which is 30/10 of a second, and then turn the motors off. And this number is the power level. And it goes from 0 to 7, where 7 means the motor is all the way on, and 0 means the motor is completely off. Now this is a bit of a trick because this motor doesn't actually have any speeds to it. If you apply voltage to it, it's on. There's no just giving it half as much voltage and expecting it to go half as fast. It doesn't work that way. So if we want the robot to go at half speed, we'll have to do a trick. Can anybody think of a trick we might use?
You incrementally turn it on and off at the same amount of time repeatedly.
Yes, incrementally turn it on and off repeatedly. So if I'm walking, I'm the robot and I'm coming toward Tony.
Stop. Go.
Oh, it's
that
red light,
game.
green light.
Yeah, red light, green light. Same game, red light, green light.
Not
Yeah.
So the computer that's on that circuit board is going to be controlling the motors just like that. And it's going to be really smooth though. It's not really jerky like when I was walking just a second ago because it happens hundreds of times a second. It's turning on the motors on and off so fast that we'll just see the robot going at half speed.
And that's a really good point. What he said is that things happen so quickly, that's why we have this oscilloscope. Like a heartbeat you can hear, right? You can hear your own heartbeat, beep, beep. This thing goes so fast, and that's why we need this oscilloscope to make sure this is working right.
Right, because it helps you see things that you wouldn't have been able to see otherwise. So if we were to draw a graph of the voltage going to that motor, so I actually should have looked up how much voltage this motor needs. Let's just say it's 6 volts. And this is 0 volts. So as time goes on, what would this graph look like? So let's say at t equals 0, we start off at 0 volts, and then we suddenly jump up to 6 volts because we've turned on the motor. So we let it go for a little while, and then we turn it off, so the voltage drops down to 0. We let it go for a little while, and we turn it on. So it makes this pattern like this, and we'll actually be able to see this on the screen of the scope. And can you guys see these little graphs here?
Yeah.
So you notice these ones here have really narrow peaks. We only turn it on for a short time, and then we drop it down. And then we go along, and we only turn it on for a short time, we drop it down. So that would be a really low speed, right? If we only let the motor go for a tiny amount of time and then shut it back off, and that's what the graph would look like if we were at a low speed. And all the way up at 7, we'd expect it to be on, and 6, on most of the time, and so forth. This technique of using the width of your signal to make something happen in the real world is called pulse width modulation. We're actually going to measure it now. Actually, do we want to, you know what, do we need to measure, or should we just risk Tony's life? Let's go ahead and, let's just risk it.
All right, first aid ready?
All right.
Yeah, first aid ready.
Ian, I hope this works.
Yeah, me too. You know what, I'm going to go ahead and test it anyway. I'm glad I decided at the last second to test
Thanks,
it.
Ian. I feel a lot better. Let's check on this oscilloscope to make sure we got the power set right here.
So it looks something like this. And we can actually see how many volts this was now. So if this is 0 volts here, and it's 5 volts per division, and we're just a little over 5 volts, so I wasn't off in my totally wild guess of about 6 volts. It's a little more like 7. You can actually measure that more precisely, but you can see that it's not on half the time and off half the time.
Yeah.
It's on most of the time and only off some of the time.
Do you guys see that?
Yeah.
See the difference of that?
And not only that, we can actually get a measurement of that. We can say add measurements, and we can pick positive duty cycle and say okay. So about 84% almost.
And so for my safety, I needed 50%. So, Ian, thanks.
Yeah. So the oscilloscope caught a problem. Now we have to decide, is the hardware turning the motors on for too long, or is there a problem with the program? And now I'm actually going to look at the program that is driving this.
So there were 2 parts to this. One is the code that's been written by somebody. That's what he's going to check. But then we're also going to double check the code on the oscilloscope to make sure what he thinks he's coded in is correct.
So this is kind of a small screen, so we've blown it up here. But basically, this number here was supposed to be a 3. And we look at it, it's actually a 6, which is almost all the way on. So I've got to, for the first time ever, operate a mouse upside down.
This is on film too, so this is happening.
Yes, for posterity.
Yeah.
Awesome. And now we need to download the new program to the robot.
So you make it
There.
turn, there we go. So you sent the new code into the robot.
I did. So now we should be able to hook it up and measure it.
So now we're going to double check what he just did. He changed it from 6 to 3. See if he really did it.
And see if the duty cycle actually changes. So we're going to hook the scope back up. So we can see now the duty cycle is 42%, a little less than half, which you'd expect if it's 0 to 3 out of 7. So we would expect now the robot to go a little slower.
Do you guys recognize this here? That's what we're shooting for, and now we check it on the oscilloscope, and it's like pretty dang close to that. It has a little more curve to it because the power kind of eases off in a minute. It doesn't go off on. It kind of eases in and off.
Are you feeling lucky?
Okay, I feel a little better about this. We'll check the code.
All right, put the eyes down on the table. Oh yeah, I've switched places. Now that I've proven that I can't program a robot, right? Oh, it's backwards. Look at that.
I'm completely safe now.
Yeah. Maybe we should just leave it that way. This happens to us every time we rehearse this too. You'd think I'd learned which way the connectors go by now. There we go. All right.
Okay,
All right, let's see how it
hoping for the
goes.
best here.
And it's look at that!
It actually worked.
So
Pretty good, right there.
I think Tony has something he would like to say to the oscilloscope.
And this
Right here?
one. Thanks, oscilloscope.
So this is the kind of thing people use these things for.